well as possible. So the first thing we're going to talk about as we intro thermochemistry is energy. We're going to define it, and we're going to talk about the different types of energy, kinetic and potential energy. So energy, with its most basic definition, can be defined as the ability to perform work. The ability to perform work, or sometimes you can say, or produce heat, if we're talking especially about chemistry, since we talk a whole lot about thermochemistry. And you will talk a lot more about thermochemistry in AP Chem. They actually just finished up their thermo test in AP Chemistry. So I had some students in here studying for that the other day. The International Systems Unit of Energy is going to be joules. So when we talk about energy and we try to calculate the energy or the enthalpy change of a reaction, as we are going to do today, you will see joules, capital J, or kilojoules, which is just that little kilo prefix, and the capital J for joules. If you're talking about the law of conservation of energy, you can state that energy cannot be created or destroyed. But energy can be transformed into different types of energy. So we can't create it or destroy it, but we can transform it from one kind of energy to another. And all the different types of energy that we talk about, or that you will talk about in the science class, can be widely sorted into two categories. And those are the categories of kinetic and potential energy, which you may remember from middle school. Kinetic and potential energy, they talk a lot about that, I think, in 8th grade science. And so here's some forms of energy that can be sorted into kinetic or potential. We have light, sound, thermal, mechanical, and electrical energy are all forms of kinetic energy. Things like nuclear, chemical energy, gravitational, the energy of position, and elastic potential energy are all types of potential energy. In chemistry, we talk a whole lot about chemical energy when we're talking about we're talking about potential energy, the energy stored in bonds. And just like I said, energy can be transformed. You can transform chemical energy into the energy of motion. You know, this is what your bodies do when you eat food and then you go do things. Plants can transform light energy into chemical energy through photosynthesis, and so on and so forth. There's all sorts of different types of energy transformation. So if we move down here, we're going to talk a little bit more about kinetic energy in more detail. Kinetic energy, or capital K, capital E, as you can abbreviate it for shorthand, is the energy of motion. So think about movement and kinetic energy. For chemistry, that means we are talking a lot about the movement of particles. And unless a substance has reached the temperature known as absolute zero, aka 0 degrees Kelvin or negative 273.15 degrees Celsius, then we say that there's always still going to be some motion, okay? There is some molecular movement present as long as we are not at absolute zero. So even in substances that are in the solid state, for example, the particles in those solids, like the ice cubes in your fridge at home, for example, the particles in those ice cubes are still moving, even though they are in a solid form, because your temperature in your freezer is not at absolute zero. And that's a nice little lead-in, talking about temperature a little bit, is a nice lead-in to the comparison between the two things, temperature and heat. Because I know we use temperature and heat interchangeably a lot in our everyday lives, just when we're talking about, you know, how hot it is outside, for example. We use those things to mean the same thing, but they do have separate definitions in science. So we're going to go ahead and define those. Does anybody remember from another class maybe what temperature is a measure of? Not exactly. A lot of people think that it is just heat. Heat is actually the transfer. Yes. It is the molecular movement itself, yes. So if you are talking about temperature, we are talking specifically about how fast the particles are moving. So temperature is a measure of actually the average kinetic energy of the particles of a substance. The average kinetic energy of the particles of some substance. Heat, on the other hand, is a transfer. It's the actual transfer of energy from one substance to another. So heat, which is oftentimes abbreviated with the letter Q, is the energy transfer from a substance with a greater temperature to a substance with a lower temperature. So this is why you don't want to touch something that has a really, really high temperature, because the tendency of thermal energy is to move from an area of higher thermal energy. Average kinetic energy of particles is the temperature measure. So if you have an on average higher kinetic energy in that other substance, that energy will move to the substance that has the on average lower kinetic energy of particles. And so that's why if you touch like a really hot stove, for example, that is why you feel that pain. That is the transfer of the energy going to your body. And last little thing here on this page is just an FYI. We're going to talk about enthalpy today, which is oftentimes abbreviated with a capital H. Delta H is change in enthalpy. And change in enthalpy is the standard that is referring to the standard heat change of a specific substance/reaction if pressure is constant. So this term is often used interchangeably with heat. If we talk about like the heat change of a reaction, people are typically talking about enthalpy. We'll talk a little bit about enthalpy today when we look at potential energy diagrams, as well as when we do some stoichiometry calculations. What questions do y'all have on this first page before we go to the next one? Cool. Then we're going to go ahead and flip to page 3 of our notes. We're going to talk about the 3 different ways heat can be transferred. We have heard these before in our lives in a previous science class, I'm sure, but I'm just going to remind us what conduction, convection, and radiation are referring to. These are all processes that can transfer thermal energy, aka what is sometimes referred to as heat. So with conduction, you can see conduction, convection, and radiation all illustrated in this image. With conduction, we are talking about molecules that are able to collide directly with one another. In order for thermal energy to be transferred via conduction, substances must touch. So substances must touch in this type of thermal energy or heat transfer. So you can see the example here, the person's hand on the handle of the pot. Hopefully that pot handle is not hot, it is insulated, but that is a mechanism by which thermal energy can move across just the physical touching of 2 objects. The second one we see pictured here by these little arrows is convection. So convection is the heat transfer by movement through a fluid. And technically that fluid can be a liquid or a gas. So you can see this happen in air and also in liquid substances like water. So in this pot that's being heated, basically the heat transfer is happening because as the water at the bottom gets really hot, in the process of getting really, really hot, heating up and getting a lot of thermal energy added to it, it's going to become less dense as the molecules spread out more. As it becomes less dense, it's going to rise up to the top, and the cooler, more dense water that's more tightly packaged together in terms of the particles is going to fall to the bottom of the pot down here. So that's why when you hear people say like hot air rises or hot water rises, it's because it's less dense. It'll rise up, and then when the cool stuff sinks to the bottom, then it itself can potentially be heated up as well. So that is convection. movement through a fluid, the thermal energy transfer there. And the last one is radiation. So radiation here is represented by these little arrows, these little squiggly lines. Those are electromagnetic waves, is what these arrows are representing here. So radiation is a process in which energy is transmitted, thermal energy specifically here, is transmitted as electromagnetic radiation waves. And that's what our sun does. That's how we get, a nice warm temperature here on Earth, is the sun is actually transferring thermal energy through electromagnetic radiation waves. They reach the planet Earth and warm us up. So those are the three types of heat transfer. Any questions there? Cool, and we're going to go ahead and jump into our potential energy discussion, and on the next page we'll talk about potential energy diagrams. So we're going to start applying some of this knowledge to some diagrams and some analysis. So potential energy, or capital P, capital E for short, bless you, is the stored energy of position. The stored energy of position. So it's potential, it's stored. For chemistry, this is referring to energy trapped in the bonding structure, or IMFs. Okay, so energy trapped in the bonding structure, you think about, in bonds, we have intramolecular forces, holding atoms together, holding bonds together, and then we have these other things called IMFs, which are short for intermolecular forces. So IMFs, or intermolecular forces, are forces between molecules, and intramolecular forces are forces within molecules or compounds. So we'll talk more about IMFs when we're talking about phase changes and stuff, because IMFs are actually what are being broken when you have a substance going from, say, a liquid to a gas state. We'll talk more about that later this unit. But when we are, of course, talking about potential energy in chemistry, we're talking about the energy stored in bonds, or stored in, the fact that there's forces between molecules. So when chemical reactions or phase changes occur, the potential energy of bonds or intermolecular forces can be transformed into kinetic energy. So reactions can break and make bonds, and phase changes can cause some forces, for example, to be meddled with, to be pushed. We can push molecules apart, or we can allow molecules to come back together in a phase change. And just a FYI, phase changes, we'll talk more about these later this unit, but this is something like a substance going from a liquid to a gas. Or if you have a substance going from a liquid to a solid, water freezing, that is considered a phase change. It's a change in state or phase, as they're sometimes called, are phase changes. So reactions or phase changes can cause energy to be transformed. We will see energy transformed in those situations. And just a little note as we jump into energy changes in chemistry and we start looking at potential energy diagrams. When we look at our calorimetry calculations next class, this will apply more to that concept. But we actually can't feel potential energy. So we can't really feel or make a direct observation necessarily of potential energy. We will, when we look at our calorimetry calculations that we're going to do next class, for example, we'll be able to make inferences about changes in potential energy by observing changes in kinetic energy. So that will make more sense when we go over calorimetry next class in those calculations. Any questions there before we get into these energy changes and potential energy diagrams? Okay. So when we're talking about energy changes in chemistry, we're going to talk a lot about reactions. When reactions happen, energy changes are happening. Energy is being transformed, it's being stored or released depending on the reaction. And when we are talking about bonds or IMFs in reactions or in phase changes, we say that energy is required to break bonds or intermolecular forces. We have to put in some energy to break a bond or to break a IMF. On the other hand, when a bond forms or an IMF forms, energy is released. And I know this seems counterintuitive because I know y'all just finished biology last year and you're all like, well, my teacher told me that when you break ATP down, we release energy. That is a very simplified version of what is happening. When you look at things, you get into the nitty-gritty of chemistry, what is actually happening, anytime you try to break a bond or an IMF, you are going to have to put energy in order to break it. Think about like a pencil. If I try to break a pencil, I'm going to have to exert some force to snap that pencil in two. When bonds form, though, or when IMFs form, we are actually going to release energy. So I know that's hard to remember, so I have a special saying to help us remember that, and that is the saying, it takes to break and freeze to form. So it takes to break and it freezes to form. So it's going to take energy to break a bond or an IMF, and energy will be released or freed when we form a bond or an IMF. So if you remember, takes to break, freeze to form, hopefully that will do a lot of the mental legwork for you in remembering how energy changes work in chemical reactions. And there are specifically two types of energy changes that we are going to zoom in on and really look at in greater detail here today. And those are endothermic and exothermic reactions. So we can say that energy changes can be endothermic or exothermic. And I kind of did not write that clearly, but there is an R in there. Okay, so make sure you've got that written down, and then we'll start talking about potential energy changes on the next page. Okay. So on page 4, you see some diagrams, and don't let them intimidate you. We are going to break them down and talk about what everything means here. And we're going to learn, how to draw them as well if we need to, if we're asked to draw them. So this is what is called a potential energy diagram. And you have your two axes here. On the y-axis, you have your potential energy in, a lot of times it will be in kilojoules. Sometimes it's in joules. And then you have the reaction pathway. So how far along in the reaction are we? And this first diagram that you see here goes along with an endothermic reaction. It's the potential energy diagram for an endothermic reaction. In an endothermic reaction, energy is needed, the energy that is needed to break the bonds in the reactant, the energy needed to break the bonds in the reactant is greater than the energy that is freed upon formation of the products. So in any chemical reaction, as you make the transition from reactants to products, the reactants, in order to get to the products state over here, we are going to have to break bonds in the reactants. That's going to take energy. And then when products are formed, that will release energy. In an endothermic reaction, the energy needed to break the bonds in the reactants is greater than the energy that is freed upon formation. What that means is that energy is entering this system, as we say. You can remember that energy is entering or being put in because endo also starts with en, just like enter. Thank you, ma'am. And so there is a transfer. What's up?
I'm taking my notes from this.
Okay, so energy is entering the system, there is a transfer of energy. There's a transfer from the kinetic energy of the surroundings to the potential energy of the system. So some of the kinetic energy of the surroundings is going to be transferred to potential energy. It's going to be transformed into potential energy. It's going to be stored in the bonds of the products. So essentially what you see here on this diagram, you see the reactant starting over here at this lower potential energy than our products. Our products are higher up on our curve here. The reason they're higher up here, if you look over to the side again, our y-axis is potential energy. There is more potential energy stored in the bonds of the products here than in the bonds of the reactants. There's more potential energy stored in the bonds of the products here than in the bonds of the reactants. We can see that because our reactants are lower on this diagram in terms of potential energy. So that is what we mean by an endothermic reaction, okay? Energy is being put in, so you can see the products are at a higher potential energy level because we have stored some of the kinetic energy from the surroundings. We've transformed it into potential energy, stored it in the bonds of those products. So verbally, what we say here, we say that energy is absorbed or gained by the system. Energy is absorbed or gained by this system. Observationally, if I were to go touch a beaker that contained a chemical reaction, there was a chemical reaction that was endothermic, I put some reactants in and I start an endothermic reaction in this beaker. If I were to go put my hand on that beaker and touch that beaker is going to feel cold. It's going to feel cool to me. It's going to feel like there's a drop in temperature. Because that reaction is taking in energy, I would perceive that as a cold temperature because some of the thermal energy from my fingers is, leaving my fingers, being pulled away from myself as I touch that reaction that's drawing in kinetic energies from the surroundings. So, for example, if you go touch ice and then you're touching the ice and your fingers feel really, really cold and you feel that really, really cold temperature, then the reason why the ice starts to melt is because melting is actually an endothermic process. So we'll talk more about phase changes later in this unit, but the reason things feel cold to you is because they're drawing thermal energy away from your body to whatever is at a lower temperature. So these reactions, observationally, these things feel cool. Numerically, when we start calculating these things, when we calculate enthalpy, anytime you have an endothermic reaction, the enthalpy value is going to be positive, some positive number of joules or kilojoules. Okay, some positive number of joules or kilojoules. The important thing here is that it's positive. That positive indicates to me that this is an endothermic reaction. And if you were to write out a reaction and include the energy in the actual reaction itself, the written reaction, you would see the heat or the energy included on the reactant side of the equation. Letting you know that we're putting in some energy, we're putting in more energy than we get out of this reaction. It's an endothermic reaction for you. And so I'm just going to make a little note over here as well, since we talked about numerically that this is going to be a positive value. That makes sense. Our reactants are going from a state of having lower potential energy to having more potential energy. They increased in the amount of potential energy stored within those bonds. That is a positive enthalpy change. Y'all with me so far? What questions do we have? Okay. Then let's look at the other type. Uh-oh. Always with the light. Okay. So let's look at the other exothermic reaction. This is the opposite of endothermic. So here's a diagram associated with an exothermic reaction. In an exothermic reaction, the energy needed to break bonds is less than the energy that is freed when new bonds are formed. So when we look at our products in comparison to our reactants over here, for example, we will see, if you look at the potential energy over here, this is the reactants, they have more potential energy than the products. You could say there is less potential energy stored in the bonds of the products than in the bonds of the reactants. Okay? There's less potential energy stored in the bonds of the products than in the bonds of the reactants. That is the case because in exothermic reactions, energy is exiting the system. So energy is leaving, energy is exiting the system. You can remember that because exit starts with EX, just like exothermic does. So there is a transfer from the potential energy of the system to the kinetic energy of the surroundings. Okay. The transfer from the potential energy of the system to the kinetic energy of the surroundings. So some of that potential energy that was stored in the bonds of the reactants was transformed and released as kinetic energy to the surroundings, and the energy that was released, of course, from breaking those bonds is more than the energy that, the energy that was needed to break the bonds. I talked myself into a circle there. The energy that was needed to break the bonds of the reactants here in an exothermic case, an exothermic reaction, is going to be less than the energy that is released upon the formation of bonds in the products here. And so as a result, we say, there's less potential energy stored in these bonds than there were in the reactants. Energy was released, energy exited the system. So we say energy is released or lost by the system. Okay, energy is released or lost by the system. Exothermic reaction, energy is exiting. That energy being released by the system, to us, if we were to go touch a beaker that had an exothermic reaction going on in it, that beaker would feel warm, okay? That beaker would feel warm. Because that reaction is releasing kinetic energy to the surroundings. Remember, temperature, or high temperature, which we perceive as, warm, that is going to increase if there's more kinetic energy being released to the surroundings, because temperature is just a measure of average kinetic energy. So that feels warm. Numerically, if we were calculating an enthalpy change, the delta H is going to be some negative number of joules or kilojoules. Whatever energy unit you're using would be negative, which makes sense over here. You look at the the energy change, the amount of potential energy in the reactants, is greater than the amount in the products. So the potential energy stored in the products decreased. We call that a negative enthalpy change, an exothermic reaction. If you were to write out a reaction and include the actual energy amount in the reaction, which you'll see how we can do that on the next couple pages, you would see heat or energy would be included as a product. Since energy is released, the heat, the energy, over here it would be included as a product, since it is being released to the surroundings. Okay. Now I know that was a lot. On the next page, I want us to kind of apply some of this thinking to some actual examples, because that's what you would be asked to do on, a progress check or an assessment. Does everybody have down what they need from this page before I flip over? Cool. And we're going to go ahead and flip to page 5 over here. So we just looked at some potential energy diagrams, some examples. We're going to analyze some potential energy diagrams down here. But before we do that, I do want to define some of those terms that we saw over here: activation energy, activated complex, so on and so forth, in order to make sure that we know what's going on. So activation energy is oftentimes abbreviated as capital E with this little a subscript. This is the energy needed to start the reaction. This is the energy needed to start the reaction, aka to break the bonds of the reactants. Activation energy is always positive. Always going to be a positive value, because we're putting in energy to break bonds. Any chemical reaction to get from the reactants to products, they're going to have to break bonds at some point in order to rearrange into what will eventually be the product. So we got to put some energy in to break bonds. It takes to break. The activated complex is that top part of the curve we saw in that potential energy diagram. So I'm going to write that this is the top of the curve. Top of the curve. This activated complex is the transition state, the transition where bonds are broken but haven't yet reformed into our product compounds. So this is our transition where bonds are broken but haven't yet reformed. And then enthalpy, or delta H, again, on a potential energy diagram, you will see enthalpy as the difference between products and reactants. The difference between products and reactants. Oh, and it's my habit to abbreviate between like that. That means between, by the way, y'all. The difference between products and reactants. Whenever you calculate enthalpy or you're asked for an enthalpy value, you must include a positive or a negative. Okay? If you leave out the positive, I'll just assume it's positive. But if it's a negative value, if it's an exothermic reaction and you have to give me the enthalpy as a negative value, if you do not include the negative, then that would be points off, because that would be incorrect. We use the positive or the negative to describe whether or not it's endo or exo. So on our diagram down here, we're going to kind of apply some of these things. We're going to label, of course, our reactants, products, so on and so forth on this diagram. And we're also going to answer some questions about the specific reaction based on the potential energy diagram associated with it. So looking at this, we always want to make sure we label our products and our reactants. And it's very similar, of course, to an actual chemical equation. When you write the products and reactants, on which side of the arrow do you write the reactants in a chemical reaction, y'all? The left. The left. So on a potential energy diagram, you are going to write reactants on this far left horizontal line. So this is where reactants go. This is the potential energy of the reactants. The products go on the right horizontal line. This is the product. Thank you. So reactants on the left, products on the right, just like when you write a chemical reaction. The activated complex, what do we say? Where's the activated complex going to hang out, y'all? The top of the curve. So up here, this is the activated complex. Top of the curve. The activation energy, that's the energy needed to start the reaction, okay? So that's going to be from our reactants to our activated complex here. So from here, this is where, our activated complex is there. This is where our reactants are here, okay? The activation energy here this is the energy we have to get to put in to break bonds to get from our reactants to our activated complex. That's our activation energy. And the last, and if you want to make a little note, maybe, between the reactants, this is between the reactants and the activated complex. That is your activation energy. The enthalpy of the reaction, we said, is the difference between the products and reactants. So I'm going to make sure I know, this is where my products are, this is where my reactants are. My enthalpy, my delta H, is going to be there. Again, difference between products and reactants. This is the difference between reactants and the activated complex. So activation energy, enthalpy. Activation energy will always be positive. Enthalpy can be positive or negative. It just depends on if it is an endothermic or an exothermic reaction. So we have all that labeled. Any questions about labeling? Okay. So based on this, I see that my reactants have more potential energy than my products. And so what that is communicating to me here is that going from reactants to products, some of that potential energy was transformed into kinetic energy and was lost. When energy is lost or released from a reaction, what do we call that reaction? Exothermic. Exothermic is energy is released, okay? So going from reactants to products, that enthalpy change was negative. Exothermic. So energy was released because some of that potential energy stored in the bonds was transformed into kinetic energy, was released, given off. The delta H of the reaction, the value here for the reaction, we can look at that and figure it out numerically by just looking at our y-axis. We're going from 40 to 20. So that's a change of how much, y'all? 20 joules, perfect. We need to use a unit. Love that we're adding units. 20 kilojoules. Because this is exothermic, because we're going from 40 to 20 also, this is a decrease, we must include the negative. This is exothermic. Okay, we have to include the negative for the delta H for it to be correct. Since it is exothermic, energy is released, given off. Is this going to feel hot or cold to the touch, y'all? Hot. This will feel hot to the touch. And since energy is released, would we consider energy to be a reactant or a product in this reaction? A product. If energy is released, it's going to be a product. It's a product of the reaction. And the very last thing is the activation energy. Okay? We're going to do a very similar process that we just did with our enthalpy. We're going to look at our values here. We're going from 40 to 100. So that's an increase of how much, y'all? 60. It's an increase of 60 kilojoules. And activation energy is always going to be positive. Okay. What questions do we have about how we tackled that? Okay. Then for the second example, I'm going to go ahead and ask y'all to try that one. Try and label and try and figure out these things based on the information you're given here, and then we will go over it. Okay, so let's go ahead and go over this. I'm going to go ahead and fill in the little labels, since hopefully y'all were able to do that. Okay, so hopefully y'all were able to get those labels in. Double check yourself, make sure you did though. Here we have a case where our reactants are lower in potential energy than our products. So what that is telling me is that we're getting some potential energy stored in the bonds of our products. There's going to be more potential energy stored in the bonds of our products than there were in our reactants. Would this be an endo or an exothermic reaction? Endo. Very good, y'all. Yeah. It is going to be an endothermic reaction. So if it's endothermic, was energy absorbed or was it released? Absorbed. Endo. Absorbed. Taking in. What is going to be our delta H for this reaction? Does anyone want to give me that one? 10, yeah. No, that is it. Yeah, it's 10. So 10, is it going to be positive or is it going to be negative? Positive. Plus 10, and then kilojoules. Okay. Would an endothermic reaction feel hot or cold to the touch, y'all? Cold. Very good. Cold. And would energy be a reactant or a product? Reactant, right? We're putting it in. We're absorbing it. And then last but not least, does anyone want to try and share what the activation energy is? Plus 40. It is. Plus 40. Very good, y'all. So hopefully y'all were able to get all of those correct. Any lingering questions there? Okie dokie. Then let's go ahead and look on this next page. I'm not going to do all of this with you. I think y'all can figure this out based on the previous examples we did. But I do want to show you how you would go about drawing a potential energy diagram when you are given the energy of the reactants, products, and the activated complex. Basically what you can do with this information is you can make yourself some little guidelines and then you can draw your curve. So here we have our energy of our reactants. We are told is 150 kilojoules. So, I want to start my reactants at this 150 kilojoule energy. The energy of my products is going to be 250 kilojoules. So, 250 kilojoules is here. So I'm going to end somewhere over here. And then I need to add in my activated complex so I know how tall to draw my little hill in the middle. My activated complex is 350 kilojoules. So if I go over here, I get 350. There's 350. So we're going to have, a little horizontal line for our reactants and a little horizontal line for our products, and then we just draw our hill, right? So draw ourselves a little hill here. And there you go. You've drawn yourself a potential energy diagram using the information provided. Any questions there? Cool. I will let you answer these on your own. If you want to check with my key later, you're welcome to do so. But I want to get more into how we would answer questions when we're just given an equation, for example. And then we'll do some stoichiometry. So energy changes of reactions. Down here, I have a equation of a reaction. What type of equation specifically is this, y'all? Combustion. Very good. We remember our reactions. So combustion. And I noticed what's different from what we've seen previously when we write reactions is that I now have this little energy amount included over there. Wild, right? So our energy is a product in this reaction. So what that's telling me is that in the process of this reaction, energy was released. It's included on the product side because energy was released. So if energy is released, is that an exo or an endothermic reaction? Exo. This is an exothermic reaction. Energy was released. And the energy that was released is exactly this much, 2220 kilojoules. For, if we react 1 mole of this, that is, and 5 moles of this together, we would get this much energy released. And so our delta H for the reaction is this amount. Since it is a exothermic reaction, we do put a negative symbol. This is exothermic. Okay, so we do put that little negative symbol in there. And so if we wanted to draw out a little potential energy diagram for this reaction, here's our potential energy in kilojoules. Here's our reaction progress. We could draw just a basic reaction, just a shape. I'm not looking for, a perfect thing with, labeled axes like we had up here. We know what the amount of energy that's released, but we weren't given the amount of energy of the reactants and the products. So just looking for a general shape. We know since energy is released, that means that our products have a lower amount of potential energy than our reactants. Some of the potential energy stored in the reactants was released as kinetic energy. That's why we have this exothermic reaction here. So the overall shape of an exothermic reaction curve is this, with the products at a higher potential energy value than with the reactants at a higher potential energy value than our products. So that's just a general shape. And so looking at this, we see very clearly that the reactants are going to contain more potential energy. We have the opposite case for this next example. We have the opposite case for this next example. I see in this example, I have the kilojoules over here listed as a reactant, okay? So if we have energy listed as a reactant, is that an endothermic or an exothermic process? Endo. It is endo. We are putting energy in. Energy is a reactant because it's being added into our reaction here. So is energy absorbed or released? Absorbed. Absorbed and exothermic. Hopefully you've noticed a pattern with exothermic and released going together and endothermic and absorbed. So the delta H for the reaction, we are given this value here, 180.7. Since we're adding it in, it's being absorbed, it is positive. This is endothermic. Okay? If I were to draw just a generic looking curve for this specific reaction, we could label our axes like so, and we can draw our very basic shape that we associate with an endothermic reaction. So, do the reactants or the products contain more potential energy in this case, y'all? The products. Very good. What questions do we have about that? Then the last thing we're going to do is we're going to just do 3 practice problems together on this back page. This is where the stoichiometry I was talking about is. We're going to do these first 3 examples, and then I will give you the answers for the other 2 so you can do them on your own. So with enthalpy changes, we can actually use stoichiometry, everyone's favorite thing, I know, to calculate the energy changes involved with the specific amounts of different substances. Instead of using a mole to mole ratio today, though, we're going to be using a mole to kilojoule ratio. So I'm going to show you how to do that. So in this first reaction, we are told to calculate the heat change in kilojoules when 5.66 moles of carbon disulfide is formed. Or that should be are formed. We are given the reaction, as well as, very nice of them, to just put it where it goes in the equation. So just looking at the fact that this energy is a reactant here, is this going to be an endothermic or an exothermic reaction, y'all? Endo, yes. We are putting this in. It is endo. So we are going to see a positive delta H associated with our answer. Our heat change will be a positive delta H because of this endo fact here. And this amount is what we're going to use to help us calculate, to help us create our mole to kilojoule ratio today. So when 5.66 moles of carbon disulfide are formed, that is our given. 5.66 moles of carbon disulfide, here it is, CS2. That is our given. I'm going to go ahead and use the train tracks for this first problem. And in creating this mole to kilojoule ratio, what we are going to do is essentially we are going to convert from moles of carbon disulfide to kilojoules to calculate the heat change of this reaction. Okay? So how we're going to do that is we're going to use, for our mole to kilojoule ratio, we're going to grab the coefficient associated with the compound we're interested in. So in this case, specifically, what does that mean if there's no coefficient, y'all? 1. It's 1 mole. So we're going to have 1 mole. So I'm going to highlight that here too. So 1 mole, and the energy amount is the energy amount that's in your equation. So we have 89.3 kilojoules. Okay, for every 1 mole of carbon disulfide that is formed, we have to put in 89.3 kilojoules. It's essentially the conversion we just set up here. And so that's how we can solve this problem. We just do 5.66 times 89.3. Okay, so 5.66 times 89.3. You get this value. Okay, how many sig figs should our answer have? 3. Perfect. We have 3 here, so we put 3 in our answer. So what can I round that to? 505. And what's our unit? Kilojoules. And we just made a little note here that we can make this positive. If you left off the positive symbol, I would assume that you meant positive, because that's what is assumed. It's kind of like not putting out a 1 in front of this. We know something's positive if there's not a negative in front of it. So that is our heat change for that value. Pretty simple. It's just that was a 1-step dimensional analysis. Sometimes it's more than 1 step. I'm going to do some 2-step ones with you here in a second, but do I have any questions before I move on to the next one? Okay, then let's go ahead and try this next one. Okay, this is the actual same reaction as we just saw up here, so nothing's really changed there in terms of the fact that this is indeed still an endothermic reaction, and we still have a positive delta H. But in this specific problem, we are asked to calculate the heat change in kilojoules when we have 16.83 grams of sulfur. So we are going to have to do, one more step here. We're going to have to go from grams of sulfur to moles of sulfur and then to kilojoules. So over here we were able to just go from moles to kilojoules. Here we're going to have to go from grams to moles and then moles to kilojoules. So I'll go ahead, I'll use the parentheses for those of y'all who are parentheses fans here. So we have 16.83 grams of sulfur. We're going to have to do 2 steps here. So we're going to go from grams of sulfur to moles of sulfur. And then we're going to go from moles of sulfur to kilojoules. So what can I use to figure out what needs to go in this gram spot here, y'all? The periodic table. Yes. So sulfur there are 32.06 grams of sulfur per 1 mole of sulfur. And then we come and look at our equation to figure out what goes in here. Okay? So moles of sulfur, we know for every 2 moles of sulfur that go in to this reaction here, we're going to also have to put in this many kilojoules. So 2 moles of sulfur for every 89.3 kilojoules. So there's where that came from, specifically from our equation. It's a mole to kilojoule ratio. Very similar to a mole ratio. Yes, Grace? No, we don't, because so specifically here for heat changes, you don't have to put like kilojoules of sulfur, since this is just energy, and there's not like a specific element that the energy is associated with. It's just energy released from the reaction. Good question. Yes, so you just have to write kilojoules. Please do include a unit, but you don't need to write kilojoules of sulfur or whatever it might be. Okay, so if you calculate this out, 16.83 times 89.3, and when you divide it by, 32.06 times 2, you should get your answer here. How many sig figs can we put in our answer? Yeah, 4. Very good. So we can round that too. 23.44. Very nice, y'all. 23.44. And our final unit, of course, kilojoules. And if you wanted to include, that it is positive, this is a positive value. You could, if you left it off, I would assume that is positive because that's how positive numbers work. Any questions there before we do this last example? Okay. Then our last example I wanted to show you specifically because they don't include the energy listed in the equation itself. They give you this over here. They give you the heat change of the reaction, the enthalpy change here. And they ask you to calculate the heat change in kilojoules when 3.40 grams of carbon monoxide are reacted with excess iron 3 oxide. Okay? And so with this, knowing that this has a negative symbol, is that an exo or an endothermic reaction, y'all? It is exo. Yeah, exo. Negative. Think of that. That would be, you could include this here. Then, on our product side, exo. So we're going to have to be careful, since it's exothermic, the delta H is going to be negative, so we have to be careful when we do our final answer. But we are, as usual, provided a given. I'll use train tracks here for this one. We have carbon monoxide, 3.40 grams of it. And just like last time, we're going to have to go from grams to mole and then moles to kilojoules. So grams of carbon monoxide, if you use your periodic table, you can calculate how many grams of carbon monoxide are in 1 mole. So carbon has a molar mass of 12.01 and oxygen has a molar mass of 16. So just for the sake of time, it's 16 plus, so this is 16, 12, 28.01 should be your molar mass of carbon monoxide. That's how many grams are in 1 mole of carbon monoxide. And then, just like we did in our previous example, we can go grab moles of CO. We know that for every 3 moles of carbon monoxide that are reacted, we can release 26.3 kilojoules. And then my final answer, since this is exothermic, I'm going to put a little negative symbol. I'm going to do my calculation. Okay. 3.4 times 26.3. Divide that by 28.01 times 3. You should get this value here. How many sig figs can I put, y'all? 3, negative 1.06 kilojoules. Again, we put that negative there since it is exothermic. There is our answer. What questions do we have there? Okay. Then for these last two, I want y'all to try, at the very least, I want you to try this last one before I let you get your phones in 5 minutes. I want you to do this one. I want you to make note of the sign here. I also want you to notice that this one's a little bit weird. We are starting with the heat change, and we want to know the mass of solid aluminum. Okay, so this is our given here. All right, because I'm actually maybe going to move this over a little bit more in case you want to add something a little bit lower. So this is your given. This is your heat change. So figure out if that needs to go over here or if that needs to go over here on the products of the reactant side. Try that, and then I'll give you the answer along with the answer to this one for practice. Okay, so hopefully we're starting to finish up. Can somebody tell me where they would put this guy if they were to write it into the equation, the heat change? The product side, very good. Yeah, so I could pop that guy over here on the product side. And my conversion then, does somebody want to tell me what they used for their first step of their conversion? Yeah, it's kilojoules to moles. Very good. Moles of what? Aluminum. Very good. So what number do I get to put with my moles of aluminum? 2. Perfect. Grabbing that just like you need to. And then there's that. And then what do we do for our second conversion, y'all? Moles to grams. So what goes with the moles of aluminum here? 1. Can somebody tell me what they put for grams there? Yeah, 26.98. Good, good. If you calculate this, you should get this value for your answer, just for the sake of kind of wrapping up so we can get all your phones back. For this one, if you want to do this one for practice, in addition to the other ones in your practice worksheet, I wanted to go ahead and give your answer here. It should be negative 130 decimal, and then kilojoules there. So you can check your work on that later. Let me know if y'all have questions. And awesome.